In today's tutorial we will have a closer look at the alpha elimination. The most renowned example is the reaction of chloroform with potassium hydroxide as a base. Also other strong bases can be used for this reaction. And what is an alpha elimination? We have carbon as the central atom, and we try to eliminate two of those substituents, in this case a hydrogen and one of the chlorides. Chloroform is rather acidic. In equilibrium it can be deprotonated. And we will get this dichlorocarbene anion, and those three chlorine atoms with their high electronegativity will stabilize the anionic charge by induction. Of course, the potassium cation is present, and now in the next step salt formation can take place, delivering enough energy that the formation of a highly reactive particle, the dichlorocarbene, with an electron sextet at the carbon is feasible. If we don't have an appropriate reaction partner for the dichlorocarbene present, then it might dimerize and the tetrachloroethene is formed. An interesting reaction partner for dichlorocarbene are olefins, which should be present from the start of a reaction. As soon as a dichlorocarbene is formed, it can react with the olefin, for instance with cyclohexene, and then a three-membered ring is formed by adding the dichlorocarbene to the olefin. A cyclopropane, a classical cyclopropane synthesis is achieved. Another interesting reaction partner are primary amines. So the R group at the primary amine might be an alkane or an aryl group, that doesn't matter, with dichlorocarbene. That is highly electrophilic. It will interact with the free electron pair of the nitrogen. And this dipolar compound is then the next reactive intermediate. One proton will change its position, will go to that carbon, and then we have a neutral intermediate. Next step, one chloride is leaving the molecule. And now again HCl is eliminated. The HCl is of course trapped by the excess of base, mainly potassium hydroxide. This intermediate is in principle the imine of formyl chloride, and again this is rather unstable, and again the chloride can leave that molecule. And again HCl is eliminated, trapped by another equivalent of potassium hydroxide. And where we finally arrive is the structure of an isonitril. The isomer of a nitrile. A nitrile, there is the other way around. Carbon here, nitrogen there. This is a dipole. And if we try to draw a mesomeric structure that is overall neutral, this is not possible. Or it does not make sense. This would be a neutral structure, but it is not a mesomeric structure, since the geometry has changed from an sp hybridization to an sp2 hybridization. So that means this is an equilibrium, but the equilibrium far on this side. This again resembles a carbene, a highly reactive, high energy particle. These isonitriles are, well, compounds that you can handle even in bulk amounts. However, the problem with those isonitriles is that they are rather smelly. They smell like dead fish. And therefore, this reaction sequence has been used as an analytic process to prove that primary amines are present. So, if you have a compound, add chloroform and potassium hydroxide, heat it up a little bit, and this horrible odor occurs, then you knew that you have had a primary amine present. Those isonitriles are very valuable compounds for synthesis, for instance for the UGI 4 or 5 component synthesis. And the this is actually not the normal way to synthesize isonitriles. Normally, you start with an amide of formic acid, treat that with phosphor oxychloride, POCl3. You will get to this intermediate, and now this Cl minus, this chloride and iron, can substitute this whole group by an addition elimination process, and actually then you will be here by this intermediate, and in the presence of a base it will go to the isonitrile. In the next video we will discuss also an interesting reaction where dichlorocarbenes have a decisive role. It is the Reimer-Tiemann reaction. See you next time.